Hello, my name is Andrew, and today I'm going to tell you about some parallelization techniques for verifying neural networks. Deep neural networks are becoming an emergent solution to a variety of problems. Many of the applications are in safety-critical domains, such as autopiloting and collision avoidance. In those domains, it is desirable to have formal guarantees about the behaviors of DNNs. However, DNNs are hard to reason about due to their highly nonlinear nature. A feed-forward neural network consists of an input layer, an output layer, and multiple hidden layers in between. Each hidden layer consists of multiple neurons, which takes as input a linear combination of the output of the previous layer, and applies a nonlinear transformation to that input. That nonlinear transformation is called an activation function. The goal of our work is to develop techniques to efficiently reason about DNNs and obtain formal guarantees about their behaviors. In particular, we focus on DNNs with ReLU activation function, which is a piecewise linear function. So what are some of the properties that are of interest? First, there is robustness property, which comes up often in image classification. Given a correctly labeled image, the property requires that there is no adversarial example within epsilon distance to that image. Another set of the properties is more system-specific. Suppose we have a set of networks for airborne collision avoidance. The networks take as input the state of the ownership and provides advisory for the next action. We might want those networks to have the property that whenever the intruder is near and approaching from the right, the networks will always advise strong left. We can encode neural network verification queries as VNN formulas. And we define VNN formula to be a conjunction of linear constraint and a conjunction of ReLU constraints. The ReLU constraint is a relation between two variables. XB is the input to the ReLU and XF is the output to the ReLU. Let's look at an example to see how we can encode a verification query as a VNN formula. Suppose we have a small network with two hidden ReLU nodes, two inputs and two outputs, and we want to check whether P0 holds on this network. We represent each hidden node with two variables. And we can encode the neural network as a set of linear constraints, a set of ReLU constraints. The second step is to encode the property. And notice that the output constraint is the negation of the output property defined in P0. This way, the checking of whether the property P0 holds is equivalent to checking the satisfiability of the conjunction of phi n and phi p. Suppose this conjunction is satisfiable, meaning that we can find an input x1, x2, such that y1 is larger than y2. Then we have a counterexample to the original property, and the property doesn't hold. The satisfiability of VNN formulas can be decided by the Reluplex procedure. It operates by eagerly handling the linear portion of a VNN formulas using a simplex algorithm, with the hope that the piecewise linear portion of the problem is not relevant. If the problem cannot be resolved by only looking at the linear portion, we perform case splits on the values and handle the resulting cases independently. The procedure also interleaves the search with bound tightening techniques to prune search space and avoid case explosion. This procedure is implemented in a tool called Marabou. Marabou also supports a parallelization mode, and it creates partitions of the problem by splitting the input region defined by the property and the neural networks. It has been shown to be effective on networks with low-dimensional inputs, but is not effective on networks with high-dimensional inputs, such as most perception networks. In this work, we generalize the parallelization scheme in Marabou and present a parallelization algorithm called split and conquer. We provide solution for handling high-dimensional inputs and also present some other techniques useful in a parallel setting. I'll illustrate split and conquer using an example. Suppose we have a VNN formula phi. We first solve it with a small timeout t1. If it timed out, we split phi into multiple subformulas, in this case phi1 through phi4, such that the disjunction of phi1 through phi4 is equisatisfiable with the original formula phi. We then handle each of the subqueries independently and solve them with a timeout t2 minus t1. Within this timeout, some subqueries might be solved and some might time out. For those timed out subqueries, we continue to split them into subformulas. And we can repeat this process until all the leaf queries are unsatisfiable or some of the subquery is satisfiable. The split and conquer algorithm is sound and complete if the underlying solver is sound and complete. And when we split a formula phi into subformulas, the disjunction of the subformulas is always equisatisfiable with the original formula. So what are some of the open parameters of split and conquer? First, there are search parameters. For instance, how many subformulas to create when we perform a split? And what is the timeout used to solve each subformulas? On the other hand, there is splitting strategy, which is the strategy to split a formula into subformulas. And this is the focus of the rest of our talk. We explored two different splitting strategies. The first is input interval splitting, which has been explored in many previous work. Suppose we have two input variables. We simply pick one of the input variable and bisect its range. This strategy is effective on networks with low dimensional inputs. The intuition is that we can propagate the input bounds in the subformulas and fix the phases of many ReLUs, and therefore reduce the complexity of the subformulas. However, this strategy is not effective on networks with high dimensional inputs, such as most perception networks. For those networks, we propose to directly split on ReLUs. A ReLU is a piecewise linear function that has two phases. Therefore, we can create two subformulas by perform a k-split on the ReLU. Phi active corresponds to the case where the ReLU is active, and phi inactive corresponds to the case where it's inactive. This allows us to avoid splitting on high-dimensional input region. The question next is, which ReLU should we pick to split on? We refer to this decision as the branching heuristic. A good branching heuristic should split a formula phi into subformulas that are first easier to solve than phi. To that end, we propose to pick ReLUs in early layers, because by propagating the bounds of the input to that ReLUs in the subformulas, it allows us to obtain more bound tightenings and therefore reducing the complexity of the subformula to a greater extent. We also want the subformulas to be balanced in terms of runtime. This is important in a parallel setting because it reduces the amount of thread starvation. To that end, we propose to pick ReLUs with symmetric input range with respect to 0. Therefore, in the resulting subformulas, the range of the input variable to that splitting ReLU will have similar interval, which will more likely to result in similar amount of bound tightenings. We capture this idea of symmetry with respect to 0 using the notion of polarity. Given an unfixed ReLU R, where x is the input to the ReLU and is between negative L to U. We define the polarity of this ReLU as U minus L over U plus L. The upper part denotes the symmetric difference of the positive interval and the negative interval, and the denominator denotes the width of the interval. Polarity of a ReLU ranges from -1 to 1. Let's look at some examples to understand better what polarity is capturing. Suppose we have an input range that lies mostly on the positive side. The polarity of this ReLU would be a value that's close to 1. Suppose we have a perfectly symmetric input range with respect to 0, then polarity would be 0. Essentially, the more asymmetric the range of the input variable is, the larger the absolute value of the polarity of that ReLU. To optimize towards both easier subformulas and balanced subformulas, we propose the following branching heuristics. On choosing a ReLU to split, we pick the ReLU with the least absolute polarity in the earliest k layers, where k is a configurable parameter. In our experiment, we set k to be 2. In practice, we found that many ReLUs do not have polarity close to 0, and the ReLU case corresponding to the narrower interval can often be quickly resolved. This opens up the opportunity to aggressively fix those unbalanced ReLUs and reduce the complexity of the problem. And therefore, we propose a preprocessing pass called Iterative Propagation that does exactly that. For each unfixed ReLU constraint R in the formula, we assert that it is in the case corresponding to the narrower interval and tries to prove it is infeasible within a small timeout. If we are successful to show infeasibility, then we essentially fix the phase of the ReLU to the other case and eliminate the ReLU constraint. We can repeat this process until we can no longer fix any more ReLUs. Since each ReLU can be handled independently, this preprocessing pass is highly parallelizable. However, there is trade-off between how much time we put in preprocessing and how much ReLU we fixed. We conducted an experiment to explore this trade-off. The x-axis is the time to solve a set of benchmarks, and the y-axis is the per ReLU timeout in the iterative propagation. The percentage shown on the right is the percentage of ReLUs fixed by iterative propagation. As the per ReLU timeout increases, the solving time continues to decrease and more ReLUs are fixed. However, the preprocessing also becomes more expensive, and it is no longer worthwhile to do when the per ReLU timeout exceeds 8 seconds. I'm now going to present some more experimental results. We evaluated our techniques on 3 benchmark sets. The ACAS-XU benchmark consists of network for airborne collision avoidance. It has 5 inputs. The other 2 benchmark sets are perception networks. MNIST networks are for digit recognition, and Tiny TaxiNet are for aircraft localization, where it takes in an image of the airport runway captured by an aircraft and predicts the location of the aircraft on the runway. The Tiny TaxiNets are convolutional networks, while the other networks are fully connected feed-forward networks. Our best configuration uses iterative propagation and use interval splitting on ACAS benchmarks and ReLU splitting on perception networks. We compare with different baseline configurations. The first is sequential Marabou. The second is split and conquer with interval split only. Finally, we also compare with Neurify, which is a state-of-the-art neural network verification tool, which also supports parallelization. We allocate 8 processors and 1 hour walk clock timeout per job. The first figure compares the runtime of split and conquer and sequential Marabou. As we can see, split and conquer is able to solve a lot more benchmarks than sequential Marabou, which shows that the parallelization scheme we use is beneficial. We also investigated the pros and cons of input splitting versus ReLU splitting. As we can see, input splitting is only competitive on ACAS benchmarks, while ReLU splitting is almost always faster on perception networks. Here is a Kaket plot comparing different configurations. I is SNC with input splitting only, M is sequential Marabou, and SNC is our best configuration. We can see that the input splitting actually solves less than sequential Marabou. This is because in the perception network benchmarks, the input splitting strategy keeps timing out on the subqueries and ended up not solving too many. And our best configuration is able to solve more instances than Neurify. And if we have resources to do a portfolio approach, we are able to solve even more. We also explored massive parallelization by performing the split and solving in the cloud service. We use a platform called GG to deploy dynamic tasks to AWS Lambda service, which allows us to run up to 1,000 short tasks at the same time. This figure shows 3 different configurations. GG Lambda is the version where we deploy the jobs to Lambda service, and GG Local is where we use GG to deploy jobs to local machines, and the third version is the native implementation of SNC. As we can see, GG Lambda does not create much overhead and continues to scale up to hundreds of workers. This is still preliminary results, and we only conducted the experiment on ACAS networks. In summary, we presented a parallel algorithm called split and conquer for neural network verification. We proposed a ReLU-based splitting strategy and a polarity-based branching heuristic. We also proposed this parallel preprocessing path called Iterative Propagation. We also showed some promising results with the ultra-scalability of our approach. The implementation of split and conquer and iterative propagation are available at the main repo of Marabou. And feel free to contact me or any developers if you want to use our tools and have questions. The future directions include optimize the strategies for choosing hyperparameters of split and conquer, including the number of splits to create and the timeout to use for each subqueries. And we also want to improve the performance of the underlying solver Marabou by integrating conflict analysis. Finally, we want to extend the techniques to handle other piecewise linear activation functions, such as leaky ReLU and hard tangent H, where the notion of polarity can be easily extended to. Thanks for your attention.